Excellent. Well, thank you very much, Hervé. I should firstly give a warm welcome to everybody who's registered for this webinar. It's really pleasing for me to see so many people registering and wanting to listen to what I'm going to talk about. I should say thank you very much to Elizabeth, who's invited me, and thank H2O'Lyon for inviting me to present this webinar. I should also say thank you very much for allowing me to present this in English. I think my French just wouldn't be good enough, so thank you very much. That's a big relief. So I will try and speak slowly and explain myself as best as I can. So just to explain, some of you are probably wondering, you know, what am I doing in Lyon? Well, Hervé mentioned that I'm here on a fellowship. So normally I'm currently working at the University of Hull, but I'm here for 10 months on a fellowship funded by Collegium de Lyon and also H2O'Lyon, and also University of Hull have also funded part of my teaching buyout to allow me to be here for 10 months. So the project that I'm working on here is looking at recent advances and the application of new technologies in gravel bed rivers. And I'm working closely with two groups, primarily Hervé Piguet's group with the EVS here in Lyon, but also a group led by Fred Libaud in Grenoble, a group called INRAE. So it's really exciting for me. I don't think there's few places better in the world to come and research gravel bed rivers. They've got some really strong research and some really strong groups here researching that area. So the prime thing I'm interested in is fluvial geomorphology, but I'm also interested in collaboration on river ecology projects. So I know some of the people listening today are ecologically based. So I'm also interested in looking at possible collaborations there. And as Hervé mentioned, I've already got myself involved with a number of different ongoing projects listed on the slide here. In particular, it's worth mentioning some work that I've been doing in conjunction with Matthew Cattell, one of the postdoctoral researchers in Lyon. And we had a real fantastic week there just before lockdown. Matthew is looking at tracing using RFID, active RFID techniques to trace gravel particles within the Severus catchment. And what's really innovative about his work is that he's using drone technology with an antenna fixed to the drone to detect the position of the tracers. So I think this is really groundbreaking, fantastic work. And the way in which I'm kind of feeding into that is using terrestrial laser scanning to look at sediment inputs from, this is a point cloud of a large scree slope that delivers a major sediment source to this stream. And I'm also looking at connectivity of tributary junctions and looking at how those add sediment. I also spent the first week of lockdown. We were really fortunate to get permissions, myself and Barbola, another postdoctoral researcher, to look at a project based on the Allier River, looking at large wood. And this is something that I hadn't originally planned to do before coming out here, but the work on that river is really very interesting because they're using RFID tags to trace the movements of wood through the system to get an idea of wood loading. So again, I'm coming into that project using terrestrial laser scanning to look at abrasion effects on the wood, which is lodged in bars, gravel bars. But also I'm interested in looking at sediment transport processes around the large wood. So these are two large poplar trees that you can see there, up to about maybe 15, 20 meters in length. And looking at scouring effect and local morphological change. So that's just two of the projects where already I've got my fingers kind of stuck into those and gathering some interesting data. So I hope to go back and do some resurveys. So today I'm going to be talking about some work that I've been doing on a river back in the UK. It's actually a river that I've been working on since 2003. It's a river based in the Tyne catchment, in fact, the South Tyne catchment, and I'm looking at three tributaries, the main one being Thinhope Burn. So I had in my title climate change, and actually this is probably the only real proper climate change slide I've got. And I think it's important to mention this because what I'm talking about is the impacts of major floods on upland catchment activation. And what the data shows in terms of rainfall going back to the mid-1700s is that we're getting wetter winters. So the graph on the top right, the blue line shows winter rainfall. Although there's fluctuations over that period, there's a gradual increase in the quantity of rainfall that we're getting during our winters within the UK. We're also getting drier summers. However, that doesn't stop us getting extreme events during the summer. And what's important is that upland areas are likely to see greater increases in precipitation. So the effects of that gradual historical increase in rainfall, possibly linked to climate change, is likely to be exacerbated in upland areas. So those are the areas when we're thinking about flood management, we need to be interested in those areas. And the bottom graph shows flood-rich and flood-poor periods. So we're currently in a flood since about the year 2000, we're in a flood-rich period. And we are, if we look back at the last 15 years or so, we are in the UK experiencing some severe events. Perhaps the most notable being Storm Desmond back in December 2015. And this was focused, the effects of this were focused upon northwest England, particularly the upland area of the Lake District. And we saw some records broken. We saw the 24-hour rainfall record broken at Honister Pass, where we had over 340 millimetres of rainfall within a 24-hour period. And obviously that rainfall translates into impacting on severe floods, again, concentrated in upland areas. So we're experiencing wetter winters, and the trend is for drier summers, but that doesn't preclude us getting severe events during the summer. And during 2007, we had an extremely wet summer, I think the second wettest on record, and a number of towns and cities around the UK got hit. This is Hull, where I'm based at the moment, and Hull got seriously impacted from surface water flooding, and some of these images are literally about 5 minutes walk from where I actually live. So, you know, flooding is quite close to my heart in that sense. So back to thinking about the uplands then. What are the implications of this trend in increasing magnitudes and possibly frequency of flooding in the uplands? Well, the implications are that we're more likely to get catchments responding in a more extreme manner in terms of their geomorphic response. We're more likely to see situations like this. This is Glen Ridding in the Lake District, where we had local flooding in Glen Ridding, largely caused by gravel transport and gravel getting lodged behind bridges. So we need to understand how to manage these catchments that are perhaps close to tipping points, where we get these increasing extremes of flood events. We're more likely to get a more extreme geomorphic reaction in terms of how the catchment responds, producing gravel transport, and that can increase flood risk. And I think there's still a debate to be had also in terms of how we manage gravel transport, particularly in upland areas. The immediate response here was to dig the gravel out and remove the gravel, whereas gravel is important for in-stream habitat, and that's often forgotten. It's quite often the flood risk factors that overrule concerns about in-stream ecology. So we need to understand how catchments are responding geomorphically in order to inform future flood management, flood risk management in upland areas. So the aims of my talk are to quantify geomorphic response and recovery to an extreme flood in an upland stream. Secondly, to examine differential catchment sensitivity and geomorphic work in response to extreme events. And finally, to explore some conceptual frameworks in an attempt to explain the geomorphic response of upland river systems to extreme events. And the conceptual ideas that I want to bring in are these two ideas in the diagram. The top right is Wallman and Miller's ideas of magnitude and frequency and geomorphic work. And here they plot the frequency of geomorphic work, which peaks at an intermediate discharge. And the geomorphic work is effectively the amount of sediment transported by a river over a given time frame. And Wallman and Miller stated that this was equivalent to the combination of the sediment transport rate, which is curve 1, and the frequency of occurrence of a given flood. So a given flow. So what we find is that low discharges don't occur that often, neither do very high discharges. It's the frequency of occurrence of a given flow. The most frequent flow is somewhere below the mid-range of flows, below the 50th percentile flow. But the maximum geomorphic work is slightly higher than the most frequently occurring flow. So I want to think about geomorphic work in that sense. I also want to bring in Shum's ideas of equilibrium and thresholds, and also Brunson and Thorne's ideas of system sensitivity. So this plot shows how river channels can react over time in terms of geomorphic work, sediment transport. So we have undulations. Let's take a single thread river channel. It might change in very small amounts in response to single floods, but it might sort of oscillate within what we call limiting thresholds. So that means although we get minor channel changes and minor sediment transport events in response to floods, the channel configuration, the channel morphology stays constant until we get a major event. So this might be a major flood, or it might be some kind of change in the catchment, such as mining in the catchment headwaters, which might introduce a lot of sediment to the system. And we get a breaking of the threshold, and we get a switch in morphology, let's say from a single thread channel to perhaps a braided channel with a wider channel width, for example. And over time, that channel might recover back to what it was originally. So you might get a change back to a single thread channel. That's as long as you don't have a persistent change in whatever caused that threshold crossing in the first place. So the river that I've been working on, it's based in it's the Tyne system, which is the River Tyne flows out in the northeast of England at Newcastle. And I've been working in the headwaters. You've got the North Tyne and the South Tyne that join to meet the Tyne. And then I've been working in the South Tyne, but working on three sub-catchments, three small sub-catchments which drain west to east. And the largest one is the Nar Burn, which is a 17 square kilometre catchment. And then the Thinhope Burn, which is the main one I'm talking about, which is an intermediate size catchments. These are still quite small catchments, it's worth mentioning. And then the Glendew Burn, which is the smallest catchment that I looked at. So these are upland catchments. Their land use is predominantly moorland. There's very little woodland. There's a little bit of woodland on Glendew Burn, but hardly any on Thinhope Burn and the Nar Burn. So we have it's basically moorland with grasses and heather, and we have around about between a ½ metre and a metre of peat that overlies Pleistocene till beneath the peat. And so this is an image of one of the main reaches that I've been working on. And this was taken before the flood event that I'm going to be talking about. And I used to take my students to this site. When I was based at Gloucestershire, I used to run an annual field trip and take undergraduate students to the Thinhope Burn every September, October. And the reason why I took them there was because it's a fantastic site for looking at evidence for river channel change over the Holocene. It's a catchment that Barbara Runsby worked on for her PhD, and what she looked at was river channel change over the Holocene. There's a beautiful set of river terraces showing how the river responded to wetter phases in climate over the Holocene. And there's also flood deposits, boulder berms, which were deposited on top of some of those terraces. And what Barbara did as part of the PhD was she used lichenometry to produce lichen growth curves using this grey-coloured lichen called Huilia tuberculosa. And so she used the lichen growth curves to date these flood deposits, these boulder berm deposits, and she was able to date 22 different floods dating back as far as 1766. And she was also able to measure the size of the boulders, so she had the date of the berm features, and she also had the size of the material, which gives us an index of the flood magnitude. So this is one such berm dated as relating to a flood back in 1929. It is situated in the main reach that I've been surveying further down the Thinhope Burn catchments. And then this is a berm dated as being around about 1776, so a much older berm that's perched on top of a terrace around about 7 meters above the contemporary river channel elevation. And that's situated further upstream at the junction between the two main tributaries that feed Thinhope Burn. So let's think about the flood in 2007 then. Well, it was a very wet summer nationwide, really, and the South Tyne catchment had experienced a lot of rainfall during June. So the ground was, the peat in the catchment was already, peat is like a sponge, so it was just full of water before this event happened. But what I'm going to talk about is an event that happened on the 17th of July, 2007. So here we've got the South Tyne catchment. In this location, we've got the Nar Burn. Here in the middle, we've got Thinhope Burn. And here we've got the smaller Glendew Burn to the north. And so these are the 5 kilometre Nimrod radar, rainfall radar cells. If I just put the colour on, I hope you can all see that the brightest red cell is situated smack bang over the headwaters of Thinhope Burn and partly to the northern half of the Nar Burn. So we had very intense rainfall over all 3 of those catchments, particularly Thinhope. The maximum 24-hour rainfall was 236 mils, and the maximum hourly rainfall from that radar data was 42 mils. So this was the impact. The photo on the left was taken by a bystander, so I don't know exactly what time it was taken, but I know it's reported to be taken on the 17th of July. And this is taken at Burnstones Bridge, just about half a kilometre before the Thinhope Burn meets the South Tyne junction. And you can see, interestingly, this is an old South Tyne railway bridge. On the right-hand photo shows the river at base flow. And you can see, you can get an idea of the elevation of water here. And you can also look at the water. It's really has a very high suspended sediment concentration. It almost looks like gravy or treacle. It's very thick with suspended sediment. For this event, I'll talk a bit more about flood estimation in a minute, but we estimated a flood of around about 60 cumecs. That's compared to a bank full estimation of 7 cumecs, so quite a significant event. And from that, we're able to estimate a reach average shear stress in excess of 500 newtons per metre. So I've been saying that I used to take students to this site, and I wasn't aware that, because these catchments are not gauged. I wasn't aware that this flood had happened until we ran the field trip in late September, early October 2007, and saw this desolation, this landscape, which was completely different, disturbed compared to what we'd seen the year before. And there's lots of evidence of gravel transport and floodplain reworking. So there was large boulder clusters, boulders up to 1 metre in diameter had clearly been mobilised. There was new fresh boulder berm deposits. There was some interesting sediment transport processes going on. So there's plenty of evidence of boulders with fresh grass underneath them. So interesting things going on. I think what's happening is that the channel, a wave of sediment had been passed through the main channel, rising to bed elevation, and some of these boulders, once the bed elevation was equivalent to a floodplain elevation, these big boulders just rolled onto the floodplain. So evidence of Newtonian flow processes, because we have boulder clusters as shown on this slide here, but we also have evidence of quite poorly sorted deposition, which is more suggestive of perhaps some non-Newtonian flow processes. So the physics of the fluid changes slightly when you've got so much suspended sediment in the water column. It basically increases the density of the fluid, so it allows coarser particles to be transported. So I mentioned that we had activation of the full catchment, and this is in the headwaters. And there was evidence of quite a significant peat slide in headwaters. So this is something that happens in upland moorland within the UK and within Ireland. They call them bog bursts in Ireland. And what's happened here is that the peat has become so wet, and the water that drains through the peat starts flowing at the interface between the peat and the till. So you see Valerie Bain here, she's standing on the till underneath. And what's happened is that this big sheet of peat has literally slipped off the slope, and it's been lubricated by this water. A bit like peat surfing across this kind of sheet of water. So we had a real, in terms of what I've seen in my experience as a UK fluvial geomorphologist, I'd never actually seen anything quite like this. It was really a full activation of the sediment system. We went from this, what looked like, this was the year before a couple of years before the flood, a stable system where you've got a single thread channel, which is maybe 3 to 4 meters in wide, yet you've got these terraces and berm deposits, but they're stabilized with vegetation. So it's what we might think of as being, going back to Brunson and Thorns' ideas, you might think of it as being a robust system. And it's switched from a single thread channel, a narrow single thread channel, to this much wider channel. So a lot of these terraces and boulder berms, which had been dated previously by Barbara Rumsby, a lot of those lower berms were totally obliterated and remobilized. And we had evidence of a change in system state, a change from a single thread channel to this multi-thread system in places. And real evidence of catchment scale mobilization in terms of mainly sediment stores within the valley. So mainly those berms, those old berms and terraces were the main sources of sediments. But there was also evidence of activation from slope channel coupling zones and also peat slides in the headwaters. So these, as I mentioned, these catchments, we do have a flow gauge on the Thinhope Burn now, but at this time we didn't have flow gauges. So we needed some way of estimating the flow. So we used post-flood evidence. So there were well-preserved flood marks, strand lines, debris lines, marooned high up on the valley sides. So we were able to go back. In terms of Thinhope Burn, we surveyed in, I think, late October, early November. We did a survey up there and surveyed in the position of the strand lines. And that information coupled with cross-section data, you're able to use the Manning-Strickler formula to get an estimate of velocity, and then translate that into with the cross-section information, get an estimate of the discharge. And a year after the events, there was a European project, I think it's finished now, called Hydrate, and one of your French colleagues, Eric Gowan, came over, and Valerie Bain was part of that, and we were able to survey, even a year after the event, we were able to find quite nice evidence, flood marks in the Narburn and the Glendew Burn catchments. So we were able to get these estimates. So estimate for the Thinhope Burn, 60 cumecs. It's important to scale that by catchment size, though. So we use this thing called the specific peak discharge, which is scaled by the catchment area. So 5.5 cumecs per square kilometre for the Thinhope Burn. How does that compare with past published information? Well, it's in excess of the figure reported for Carling's Noon Hill flash floods paper on the Langdon Beck, and it falls into the range reported by Adrian Harvey for the floods in the Howgill Fells. The Narburn response, we had an estimate of 19 cumecs, so quite a bit lower, specific peak discharge of 1.1 cumec per square kilometre. And the Glendew Burn, the smallest catchment, a maximum discharge of around about 6 cumecs, specific peak discharge of 1.3 cumec per square kilometre. So how did the Thinhope Burn event, in terms of its magnitude, compare historically? So what I've done here is compare the grain size that was measured after the 2000 event, grain size in freshly deposited boulder berms, with the historical data presented by Rumsby's PhD, but also published in the Macklin et al. 1992 paper. And what this basically shows us is how is the occurrence of historically of significant events back to 1766, but also because we've got the grain size, we know something about the relative magnitude of those floods. And what's interesting is that there's only 2 other events that either have an equivalent grain size or greater grain size compared to the 2007 event. And this allows us to, so it really was quite a significant event for this catchment. So it gives us a rough estimate in terms of the frequency of this event from using this data of a 1 in 80 year event. So why did Thinhope Burn respond differently to its neighbours? Well, I suppose the easy answer is it didn't rain as much in the Glendew Burn and the Narburn. We do see that the most intense rainfall did appear to be in Thinhope Burn, and obviously the flow estimates are significantly greater. But I wanted to investigate this a little bit further, and I've used landscape evolution modelling, Tom Coulthard's Caesar Liz flood, to investigate this further. Now this model can be run at the catchment scale, and it uses, it's got top model, which is a rainfall, Bevan and Kirkby's top model, rainfall runoff model. So you need a DEM of your catchment, and you need rainfall data, ideally hourly rainfall data. And that is translated then into a discharge based upon the top model, what that gives us. The model can also be run at the reach scale, and it uses more recently the Liz flood code to simulate 2-dimensional reach scale hydraulics. So it's really quite a flexible model. It's quite useful for exploratory analysis, which is what I've been using it for, and it's really geared towards thinking about geomorphological processes. So for the catchment scale runs, I used a 10-metre resolution DEM. That might sound quite coarse, but there was a reason for that. I was using this as an exploratory tool, and I wanted to have quite relatively fast model runs so I could explore different magnitude rainfall events and the effects of that on 3 different catchments. And for the reach scale runs, I've used 2-metre LiDAR data. The rainfall data as input to this model was a slight problem because there wasn't a local rain gauge where we had a long series of data. So I've used a 10-year record as part of a spin-up process for the model of hourly data from Keswick, which is a similar altitude, perhaps slightly greater rainfall than locally in Alston. But this wasn't, as you'll see later on, it's not necessarily a problem for what I was looking at. It's more to use this as an exploratory tool. And then at the end of that series, I have used the local rainfall data derived from the 5-kilometre Nimrod radar. And then what I've done for the modelling exercises is that I've scaled the rainfall data to produce a series of different magnitude flood hydrographs for the 2007 events. So these have broadly been scaled at and this is probably quite important. There's a rainfall record, and these are the scaled discharges that result from scaling the rainfall at 0.25 times the rainfall, 0.5 times the rainfall, round about 0.75 times the rainfall, 1 times the rainfall, and 1.5 times the rainfall, and that produces a series of scaled hydrographs. So I'm looking at the effectiveness, the effects of these scaled hydrographs on geomorphic work. So we're able to look at, this is one of the things you can look at in terms of a visual output from Caesar Liz flood when it's run at catchment scale. And I've just included the runs for Thinhope here because this is the only catchment that really showed quite a striking visual response as we ramp up the flow. And you can see those, the red areas being the areas where we've got most erosion, and you can't quite see it in this image, but there are some lighter green areas that show areas of deposition. And what I can do with the modelling is that you can investigate how much sediment, what the sediment efflux is out of the catchment. So that was what I was using as a measure of geomorphic work relating back to Wollman and Miller's ideas. So I'm really interested in how much these flows, these different scaled discharges, the effect this has upon the work, the geomorphic work conducted, and that's indicated by the amount of sediment transport that is delivered out of the catchment. So this is what I presented here then. So this is the total sediment, the cumulative sediment efflux over the 10-year rainfall period with the July 2007 radar data tagged onto the end of that series. So the top graph shows cumulative sediment efflux, sediment output scaled by catchment area. For the black line is the Thinhope Burn, the red line is the Nar Burn, the largest catchment, and the smallest catchments, the blue line, Glendew Burn, to the north of Thinhope. The most striking thing is that Thinhope clearly produces massively more amounts of sediment in comparison to its two neighbours. And this is when you throw the same amount of rainfall at the catchment. The bottom graphs are discharge hydrographs. So this is what top model, which is which is built into Caesar. This is what it's estimated the discharge to be based upon the rainfall time series. And the discharge for the largest catchment, Nar Burn, we get greater magnitude discharge. We've got an intermediate magnitude discharge series for Thinhope, and the smallest kind of discharge peaks for Glendew Burn. But obviously they all show the same temporal pattern because we're using the same rainfall inputs. It's just that top model has delivered different discharge outputs, largely because we've got different sized catchments. What I should point out is that top model has actually, I think, overestimated the discharges. But again, I don't think that's a big problem because we're just doing a comparative analysis here. But overall, the top model does overestimate the discharges based upon the rainfall input. So just to the main point to take home from this is that clearly Thinhope appears to be much more sensitive than its neighbouring catchments because it's producing a lot more sediment over that 10-year period. Oh, and another thing what I didn't mention is that we get, and this links back to climatic fluctuations. At the start of the rainfall series, so between 1998 and 2001, we've got a wet period. And then between about 2001 and 2005, we've got a drier period. And then between 2005, 2008, we've got another wet period. And you can see that this is reflected in the sediment output. So we've got quite a steep rise at the start of that period relating to this wet period in the late 90s, early 2000s. And then we've got a less steep slope in terms of sediment efflux. And then again, towards the end of the series, so from about 2005, again, we've got a steep rise in sediment output, which appears to be linked to the change in the discharge regime, linked to increasing rainfall. So just focusing now upon what happened in Thinhope Burn. So this is a similar graph. It shows cumulative sediment outputs just for Thinhope this time. And I'm looking at the scaled data. So it's using the scaled rainfall data. Remember I explained this earlier. And it's showing the sediment outputs, sediment efflux for the July events. So we've got our scaled discharge outputs based upon the rainfall data, the scaled rainfall data from about the 11th of July through to about the 25th of July. So this is the event in question. This is the big event on the 17th of July, which is the first peak. But there was also a secondary event, the second peak here, which is of lower magnitude, but obviously potentially still conducted a serious amount of sediment transport. So the point to take home from this is that the lower magnitude, the lower scaled discharges, so 0.25 and 0.25, the discharges scaled upon based upon 0.25 and 0.5 scaled rainfall data, don't actually deliver that much sediment. And then there's quite a significant jump when we get to the 0.6 scaled discharge, which is the equivalent. So that's the one that produced an equivalent discharge peak to what we actually found at Thinhope Burn. So significant amount of sediment produced by that event. But interestingly, for the top two discharge peaks, so this is using the 1 and 1.5 scaled rainfall data. So this is producing discharge peaks of 90 for the blue line, and 236 QMEX based upon the scaled rainfall data. Doesn't actually produce much more sediment. So it's almost as if the 60 QMEC event somehow produces an optimum amount of sediment for the catchment. Another interesting point is that for the second flood peak, the 0.6 scaled rainfall data and the flow data from that doesn't produce much of an increase in sediment output. Yet the higher two flows do produce, so the 1 and 1.5 scaled rainfall and the flows that produces does produce a significant sediment output. So it's almost as if the first flows prime the system in that sense. What we can also do is plot the total sediment outputs against the peak flow events or the peaks of those flows for the scaled events. So what we've got here, the black line shows the data for Thinhope. So these are the peak flows for our scaled discharges. And this is plotted against the total sediment output scaled against catchment area. And this time we see, again, Thinhope Burn is producing a lot more sediment output compared to its neighbours. But interestingly, instead of the Burn, the larger catchment producing as much sediment when it's scaled by catchment area, it's actually the smaller Glendew catchment to the north appears to be doing more geomorphic work when you scale the sediment output by the catchment area in comparison to the larger Narburn, which experienced higher discharges and higher specific discharges. These curves here are analogous to the sediment transport rate curve that we find on the Wollman and Miller graph, just to note. So we also did work at the reach scale, and we've been doing some surveying at the reach scale, initially using GPS. So we started surveying here with my then postgraduate student, Andy Parker, using DGPS. And we surveyed a 500-meter reach and used the data to build DEMs. And by differencing the DEMs, you get DODs or DEMs of difference to give us spatial patterns of erosion and deposition. So that was well before the 2007 event. And then more recently, we've been using terrestrial laser scanning, and we've been using a Topcon GLS 2000, which is a red wavelength laser scanner, red wavelength LiDAR. And so we've been conducting not quite, but near annual surveys since about 2011 using LiDAR. And again, using the point cloud data derived from this to build the DEMs. So let's have a look at some of the morphological changes, and I will not dwell on this for too long. This is the reach in question that has been surveyed back since 2003. This area here, you can just see that grey area. That's the 1929 berm that I showed you at the start of the presentation. And you can see a narrow channel, but a nice, you can see why I used to take students there, a nice staircase of terraces, of really interesting catchments. And this was the image towards the end of 2007. And this is, you can see significant change, significant channel widening, and again, a change by 2012. So importantly, so these are the DEMs of difference. So this is where the DEMs have been subtracted from one another to look at the spatial patterns in elevation change. So the red areas show erosion and the blue areas show deposition. And it's the intensity of those colours that we really want to think about here. And fortunately, we had some, not for the full 500-metre reach, but fortunately for about 2/3 of that reach, we had pre-event data on how the channel had changed in its robust pre-flood state. So we're able to get an idea of how much change we might expect when the system is operating within intrinsic thresholds within the system. Here we see the changes after the 2007 events, and pretty major channel changes, new berms deposited, lots of sediment transported. We'll have a look at the volumes in a minute. Predominantly deposition, though, within the reach. The following year, 2007 to 2008, we had a dominance of erosion in the reach, suggesting that a lot of that deposited sediment had been reworked. And 2007 to 2011, we had a rough balance within the budget, which I'll show again in a minute. So I should say that data was published in a paper back in Geomorphology in 2012. So this is what I'm showing you here is the more recent unpublished data, and we actually have 2 more surveys to add on to this that I'm not reporting today. But as you see, we've got a good record in terms of trying to understand sediment flux, or certainly erosion deposition volumes through this reach. So between 2011 and 2014, those colours are still bright. There's still a lot of erosion deposition, still a lot of redistribution of sediment really disturbed by the 2007 events occurring. And then after 2014, we see that the colours begin to get a bit paler, which is suggested that there's not as much erosion and deposition operating. So let's think about what's happening on that full 500-metre reach. So what I've got here is a sediment budget graph. It's scaled by the area, by the survey area. And again, the blue bars show deposition, the red bars show erosion. And so this is the volume of erosion deposition, and it's scaled, so volume cubic meters per square meter. And we see that before the 2007 event, so 2004 here, this is our pre-event data. What I'm saying here is that the changes here are within these limiting intrinsic thresholds. So this is the normal change sediment transport you might get during a regular winter flood, maybe a 2-year event, perhaps a bankfall flood, that might not quite have a dramatic adjustment on channel morphology, but might transport a reasonable amount of bed load. But what's happened after the 2007 event is that clearly a lot of the floodplain and berms and terraces were mobilised. So what I'm arguing here is that we've had a change in system state, a state change. We've had the breaking of those intrinsic thresholds. Okay, and over time we see that there is some kind of relaxation, some sort of recovery going on. So we do have a reduction in sediment volumes over time, but certainly even by 2014, there's still a significant amount of sediment volumes being transported. And I would argue that the system still has not fully recovered. What I'm arguing here is that we have a new system state that's adjusted to this new wetter period in our climate, certainly since around about 2000, that first slide I showed showing that we're currently in a wet period. I think the system state currently is adjusted to that wet period. And until we go into a dry climatic period, it's never going to get back to what it originally was. That's what I'm arguing. So we also ran some reach scale simulations in Caesar Liz flood, initially for a 2-kilometre length of channel here. And then what I'm going to show you is this red box, which is equivalent to the reach that I've been working on. Don't have time to show you all of these runs, just to show the 60 QMEC run, which is similar to the actual events, and just to point out that we get similar patterns, which is encouraging of erosion and deposition. What we don't get is the same magnitudes, the predicted magnitudes that are predicted by the model. And I should say that the sediment transport model that's used in Caesar Liz flood, or the one I selected, was the Wilcock and Crow sediment transport formula, which is really the one to use when you've got mixtures of grain sizes that you find within gravel bed rivers. The erosion deposition volumes are maybe half or even less than half of what actually happened during that event. So it doesn't quite give us a 100% match in terms of erosion deposition volumes. I should also say that it's possible to get velocity output and even convert this with the depth information to a shear stress. So that's what I'm showing here for the different. So I've ran the model at reach scale for our scaled rainfall series again, and these are the velocity populations. So this is based upon effectively the velocity output maps, basically the raster grids which are generated by Caesar. So each cell, each wet cell returns a velocity, and what I've done is I've plotted the population of those velocities for these different events. So as you might expect, that the yellow curve is for the lowest magnitude peak, which is the 4 QMEC peak, and the mode of velocities is around about 1.5 meters per second, as you might expect for a smaller flow. Moving up to the 27 QMEC flow, we see that the mode is just below 3 meters per second. Quite a big difference between 4 QMECs. But as we increase the discharge and get to 60 QMECs and above, up to 236 QMECs, we see that there's actually very little difference in the population of velocities. I think that's quite different. This is telling us that we've almost got peak energy being produced by flows around about 60 cumecs, I think. So it exceeds that discharge much further, and 236 cumecs is exceeding it massively. We don't get much of an increase in the velocity, in the energy exerted on the landscape. I think that's quite important when we think about geomorphic work. So linking all of this back to some of these concepts once more, the Woolman and Miller idea of frequency and of occurrence and geomorphic work. So I think before the 2007 events, we had a robust system. So that relates back to Bruns and Thorne's ideas of landscape sensitivity. Robust in the sense that it needed a big event to mobilize this material in the berms and terraces, which was stabilized by vegetation. The kind of 2 to 3 year bank full event that Woolman argues here gives us the maximum geomorphic work, I don't think really applied to Thinhope Burn catchments. Okay, you get gravel transport, but it's all contained within this 3 to 4 meter wide channel. But if you get a significant event that makes the system trip over that threshold, then you get a real massive increase in the geomorphic work. And I think it needs that rarer, more higher magnitude event to actually do that. So perhaps this 1 in 80 year 60 cumec events to actually do the damage to the system. So I think what's happening in its robust state, the system behaves more like a modification of the Woolman and Miller model that was originally published by Baker back in 1977, where he related this to the way in which semi-arid bedrock and bedrock alluvial rivers responded. So he was arguing that it was the rare high magnitude floods that were the effective geomorphic agents. And that's why the sediment transport rate and the geomorphic work curve is pushed to the far end of the flow frequency curve. So it's the rarer higher magnitude events which are the effective geomorphic agents. However, when these system thresholds have been exceeded and we've got what has happened on the Thinhope Burn, we do now have a more sensitive system. It's behaving in a very different way. We have much more in a way of available sediments that isn't bound together by vegetation. So it's much more sensitive to lower magnitude flows. So lower magnitude flows can do more geomorphic work. Hence, I think in its current condition, the Woolman and Miller concept in its original form is more applicable. So I think we have to kind of move the goalposts on this system in terms of how we apply these concepts, because the system behaves very differently depending on which state it's actually in. So to conclude then, so I've done a combination of catchment scale modelling and fairly long-term field. This is quite a long study now when we think about the length of field work, where we've done high resolution surveys, a combination of that on this catchment. And the catchment scale modelling does, even though the neighbouring catchments did experience less rainfall, the modelling does seem to actually suggest that something else is going on. It suggests that Thinhope Burn, for some reason, and the questions, I think there's questions that still need answering that I can't fully answer here. For some reason, Thinhope is significantly more sensitive to flood events. And you could see that historically, just looking at the morphological landscape within that catchment, the terraces and the berms. It has been historically highly active over time for some reason. Could possibly be something to do with the availability of stored sediments on the valley floor, perhaps. The catchment scale modelling, the catchment scale outputs from the Caesar modelling do appear to indicate that the flow that occurred in 2007 perhaps appeared what I'm calling peak hydraulic output. Flows in excess of that didn't particularly seem to do anything else in terms of producing more sediments, and it didn't appear to show any increase in hydraulic energy. I think that's quite interesting. So 13 years after the event, Thinhope Burn has still not fully recovered. And I think this might have something to do with the fact that we're in this wet phase. So it's responding to climatic perturbations. And I think that's quite interesting because it links to what I was talking about in terms of river management. And we're thinking about flood defence, flood management, in flood risk management into the future, and how uplands might respond. We might need to factor this in and factor the fact in that some catchments that hadn't previously been active might at some stage quite suddenly show responsive behaviour. The 2007 event showed us a change in system state with a much greater volume of sediment transport and different channel morphology compared to the pre-2007 state. So I think the kind of Wallman and Miller concept and Brunson and Thorne's ideas of sensitivity those are very helpful concepts, but I think in this it's useful to use them in a flexible manner, because I think this particular system behaves very differently depending on which state the system is actually in. So just before I finish, there's people I should mention. So I've been working most closely over the last 6 to 8 years or so with Arved on this catchment. So Arved's not only has he been a great help on field work, he's also fed in to a lot of the concepts on what's happening on Thinhope Burn, and he's also obviously we had a paper out earlier this year where we compared some of the terrestrial LiDAR data to SFM output. So he's really had a big intellectual input to this project. So thanks, Arved. Also, I should mention my colleagues at Hull. So Tom Coulthard. So firstly, thanks for developing Caesar Liz flood, but he also had an input at the earlier stages of this work and offered some valuable advice on running the model and what to do about the fact that I didn't have any rainfall data close by. So thanks, Tom, for that. And also thanks to Chris Skinner. So Chris, not only has he helped on some of the field work, but quite importantly, he's used some of the point cloud outputs, and some of you might have come across him at the EGU, to develop virtual reality games, if you like, to try and educate people, particularly younger people, about the dangers of flash floods. And you can get some of the simulations, you can find them either on his Serious GeoGames website or on YouTube. So there's really been quite an important outreach element that's been a valuable output from this research. And finally, I should thank some other people. So I've got colleagues, mainly from Gloucestershire, but also some ex-students from Hull. So particularly people like Andy Parger, who was a postgraduate student of mine, certainly helped with the early stages of the survey work. But also people like John Hunt, Paul Kimber and Julia Webb, my ex-colleagues from Gloucestershire, all helped a lot on field trips and in the field. And then the rest of those names there are undergraduate students that either did dissertation projects with me or helped on field work in the Thinhope Burn. So some of those I think are listening today. So I've just got to say, thank you very much for all that help, and I hope you found the talk interesting. So that's where I'm going to conclude, just to show you a sequence of, this was where the 1929 burn was. You can see how it had been ripped out of images almost through to the present day. I didn't quite tag on 2020. So thank you very much. So I hope you enjoyed that. I'd be happy to take questions, as long as they're easy questions. Thank you.
Do we expect grazing or overgrazing may have any effects on bank resistance? Something which is
this
kind of region?
Although there is sheep grazing in I think there's mainly sheep grazing within the catchments. Um, yeah, it's not something I can definitely say whether or not it does have a major effect. It's not something that I would instantly think would be one of the key factors. If you looked at the system before the events, you know, the grazing didn't really have. I think, to be honest, most of the sheep are kept off fenced in and can't actually get down to the river channel. So I don't think the actual valley bottom is particularly susceptible to grazing. Thinking about it a bit further, because the tops of the valley is quite narrow and incised, and most of the farmland is actually perched up on the valley tops. So I don't think that's a major factor, Hervé.
Okay. I think John Hunt had a questions.
Thank you very much, Hervé. Fascinating. Great to see some of the sites I've been up with you, well, with the students. I had a few questions, but I'll stick it just to one. This is less site specific, but more general. Looking at what you were talking about, geomorphic work, and particularly one of the graphs through time, showing how much sediment moved. It looked to me, and you've almost covered this in your conclusions, but have you investigated the proportionality between geomorphic work and the antecedent period between events? So that looked to come out of one of the graphs you showed very clearly, that there was the longer the interval between recorded berm forming events, the more they were formed afterwards because of sediment availability.
No, that's certainly a very important factor. I think antecedents in conditioning how responsive systems are. I mean that's all factored in, I think, in terms of what's happening at the moment. The reason why the system is still in a responsive state is that it's just not had enough time to recover. So I think it's difficult to say for definite because we don't have these catchments. Well, we've only had them gauged for the last 18 months to 2 years. So we don't know exactly what's flow discharge wise. You know, with actual measurements, we can model it. But I would guess, yes, you need a long period to allow vegetation to take a foot and restabilize some of those bars and berms. And, you know, that is definitely a huge factor in determining how responsive the river channel is.
Following up Hervé's question, I think it was about grazing. One of the things that surprised me for the first time living full time in landscape not unfamiliar and different to this in the Welsh valleys is seeing the importance of peat hill slope fires in creating sediment sources. And I wonder if there's any influence of moorland fires in removing the peat cover and exposing the till that could have factored in.
Yeah, that's a good question. I mean, that's certainly, there's been papers published, I think some Manchester colleagues have published papers on that, on the kind of west side of the Pennines. And yeah, there is documentary evidence to show that peat, burning the peat does make the landscape much susceptible to erosion and peat loss. But focusing up on Thinhope Burn, during the period that I've worked there, so I've been going up there since I think the late 90s was the first time that I visited that site. And there hasn't been any evidence of burning within those catchments. And certainly, Thinhope Burn, after that event, I had a very, very good look at the full catchments, and there wasn't really any evidence of burning. I mean, I think the hydrology is actually quite complex. That's an interesting thing to mention. It's probably something that top modelling doesn't model very well. Is that you have a system of pipes flowing through the peat. So it's quite a complex drainage system. You don't just get the water flowing through the pore spaces, but you've got this water flowing at a faster rate through pipes, and then you've got water flowing in between that peat interface and the till. But going back to your question, deviating, sorry, I wouldn't say, as far as my fieldwork experience tells me, there wasn't really a great amount of evidence to suggest that burning had a major impact.
Last one, after the 1776 Burn event, you had a 7-meter incision apparent between the height of the berm. You looked at where all that sediment went.
Well, I presume it's stored in some of the terraces or berms further downstream. So I just presume a lot of it's been reworked. So that was, that's not something that was more part of Barbara Rumsby's earlier work. But I guess, most of the sediment storage seems to be, instead of thinking about the work that Adrian Harvey did in Howgill Fells, he attributed a lot of the sediments originating from slope channel coupling zones. So at Thinhope, you do get slope channel coupling, and the slopes did provide some sediment directly to the channel, but the major sediment source was material that was already sitting on the valley floor, that was stored in these berms and terraces. And it was those features that basically got reworked and mobilized.
Could you explain a little more the graph where you have the D50 on the y-axis, and the x-axis you have the time? I think perhaps you have to go back to how you date the different surfaces.
You were saying that there was some evolution, or how can you estimate, first, how do you estimate these values?
Okay, so yeah, so this most of the data here is from Barbara Rumsby's PhD work, and so she did a PhD back in the early 90s, and she's used a technique called lichenometry to date these old flood deposits that were stored in these berm features. So she's worked out the dates by creating what we call a lichen growth curve. So she's visited nearby sites where there's been a dating control. So places like graveyards where you've got gravestones, and what you do is you measure the size of the largest lichen. You have to make sure you're using the same species as you find on the morphology that you're interested in. On the gravestone, you measure the size of the largest lichen, and you plot that against the oldest date on the gravestone. And once you've measured many lichens and many gravestones, you have a large amount of data with dates, because what happens is that the growth of the lichen is correlated very closely. So the width of what we call the lichen thalli grows at a constant rate over time. And if you have a dating control, you can produce a graph of lichen size against date. And then what you do is you use that lichen growth curve to date the features of interest. So you have to make sure that your date control, your graveyard, or it might be there's plenty of old historical bridges within the South Tyne catchment that were also used, that these stone bridges have dates when they were built on. You can use that curve, you can use the correlation to estimate the date of these features. And that's what Barbara's done here. So she was able to date 22 different berm deposits dating back to 1766. And also by measuring the size of the grains in those berm deposits, that gives us just an index of flood magnitude. So that's what I've done here is I've simply plotted with the data with the red circle. That's the data of the material that was mobilized during the 2007 event. So what I'm suggesting here is that the coarseness, the grain size of the material was comparable to two of the previous highest magnitude flows back as far as 1766. Does that help explain?
Yeah, definitely. But it seems then that by the end of 18th century, beginning of 19th century, the discharge, I guess, or at least the sediment transport, but the discharge may have been similar to today. So is there really climate change in this watershed? Is not fully clear for me.
Yeah, I mean, I've not focused upon. I mean, it is. I think it is. I've not shown this, but there is a link to climate change, and that within the Macklin et al. Paper that was published out of Barbara's work, they do refer to some work by I think it was Keith Barber on Bolton Fell moss, where they were able to correlate these floods to wetter periods. So they've looked at peat, some kind of peat desiccation index, and they've managed to correlate some of these events to wetter periods in climate dating back to the 1700s. So I mean, I can't provide the exact details myself, but it has been demonstrated within that paper that there is a link.
Particles seems quite angular in the channel. I was impressed too. And do you have any idea of the distance of travel? Usually particles get rounded in the first kilometers. So roundness approach could be quite interesting for your case.
Yeah, that's very interesting. Sadly, no, I don't. We didn't have any. We didn't trace any particles. I've had some interesting discussions over the years with Arved. We've thought about. He was trying to convince me to do some RFID work. But I was always saying I don't think we'd ever find the particles. There's so much bedload transport. But now I've seen Matthew's work with the active RFID. I'm beginning to change my view on this. So sadly, I don't have any step length data. And yes, that is an interesting point about the particle shape. Some of those more angular particles may be the particles that have dropped out of till at slope channel coupling zones. I can't prove that. So it's if you looked at most of the particles that were held in the old berm deposits before the flood tended to be fairly, from what I can recall, tended to be fairly rounded in nature. But some of those real big blocky particles, there was one photo I showed where it was almost like a square block. Matthew's quite right. It is suggestive that particle hasn't travelled that far, or certainly hadn't experienced that many mobilisation events. So that might be one that's kind of recently popped out of a slope channel coupling zone further upstream, but I can't prove anything about step length.
Yeah, I think we have a good software for you to look at by imagery the roundness of particles. It could provide some good indications.
Okay, that sounds good. That sounds good.
Discuss this tomorrow. I have. Let's see. Another questions about the fluvial system and responsiveness. You did not speak about resilience. Could we expect your system is resilient or is not resilient to what you have learned here? Okay,
so I think it's just, I mean, resilience is another term I could have used. I suppose a resilient system is the same thing, well, to me, it's the same thing as a robust system. And I think the system can be considered during periods of drier climate, that the Thinhope system might be considered robust during that period. But as soon as you have this wetter phase where you've got an increase in frequency of more extreme events, it's no longer resilient, it's no longer robust. So I think every system must have some kind of tipping point, and perhaps for some reason, Thinhope Burn is closer to that threshold, closer to that tipping point. You know, in comparison to its neighbours, I wouldn't say it's as resilient to flooding as its neighbours, or I wouldn't say it's as robust as Narburn and Glendew. But so resilience is, yeah, it's a term that I could have used instead of robustness, I think.
If we continue on this point, you that your system changed roughly 13 years ago. It's not so long. If we compare this with the herbaceous encroachment, which is unusual compared to our rivers around Lyon, but here you have herbaceous, and it seems to me it makes quite a long time to re-encroach the channel. Did you survey the encroachment? Because it can be a bit long, and then your system can readapt and go back to its previous state. So I would say perhaps he has a low resilience.
Well, it might. I mean, it might well be that, you know, we need to continue the survey work into the future to find out how long it takes for the system to revert back. I mean, yeah, I was, I suppose what we would say in England, I'm sticking my arm out to say that the system has, at the moment, is in a different system state, and I'm arguing that it's not going to revert back to that original state until we have a drier period, climatic phase. But I could be wrong. I mean, we don't know until, you know, I guess what myself and Arved need to do is continue the annual surveys and see whether we get. I mean, there is some evidence of some of the bars and berms revegetating, but I still think that, you know, if we get another reasonable event within the next two or 3 years, all of that material is still going to be more easily mobilized than it would have been previously.
Oh, that's very good. We don't know is really the answer. No. So we have to, as you said, you have to continue to monitor, and you would be lucky if it's the case. We are searching to have more active rivers. Ours are less and less, so it would be great.
Yeah, it's quite, you know, in the UK, it's quite unusual to get such an active system, to be honest. So it's nice to work on one. But active systems don't go down too well with flood risk managers and the general public. They often see it as a problem rather than thinking that for geomorphologists, it's exciting, and for ecologists, it's, well, you know, it's interesting in terms of habitat and how organisms might respond to disturbance, perhaps. But for flood risk managers, they're generally thinking about protecting people from floods rather than thinking about the geomorphology.